In the previous video, we have defined curvature tensor for a Riemannian manifold. Recall that we get this Riemann curvature tensor from the Riemann curvature endomorphism. This Riemann curvature endomorphism is a 3-1 tensor, which measures the extent to which our manifold fails the flatness criterion. So what we want to do in the subsequent videos is to relate this to our discussion of curvature in the overview. Recall that in the overview we have discussed several notions of curvature. So for example, for surfaces in space, at every point P we have defined a notion of curvature in every direction, in each direction at P. And from that we got the notion of principal curvature, right? These are the max and the min amongst this direction, but they are not intrinsic. So then we mentioned the notion of Gaussian curvature and said that this product of this principal curvature, this is going to be intrinsic. We also mentioned the notion of sectional curvature, whereas for this case here, of surfaces here, we get one curvature for each curve through P. Here we get, in this case, we get one curvature for each two-dimensional submanifold through P. Now we want to unpack all of these concepts, so we want to define all of these rigorously and then relate them to the curvature tensor. In particular, in this video, we're gonna give an alternative description of principal curvatures in such a way that generalizes to higher dimension. We'll do so by introducing an operator called the shape operator. From its definition, we will see that this map here factors through the shape operator, so that this map could be described as V map to the shape operator of V, and then we take the inner product of V with the shape operator. The principal curvatures then are gonna correspond to the eigenvalues of the shape operator. Alright, so let us first define this shape operator for surfaces in space, and then we will generalize that to any Riemannian manifold. To that end, we need to first review what this map is. Recall that for every direction V here, right, this map tells us how much the surface curve in the direction of V at P. More precisely, it's defined as follows. So if I have a tangent vector here, I can look at the normal plane through P, right, and parallel to this tangent vector. Now that normal plane is gonna intersect with our manifold in the curve, which we call the normal section, right, of this plane. We thus then define the image of this vector V under this curvature map to be the sine curvature of this curve, because this captures how much the space curve in this V direction. Okay, so now to define the shape operator, we want to first find formula for this. We want to first reframe this. So how do we compute the sine curvature? Well, this is a plane curve, right? So let's say that we parameterize this so that this curve starts at P with an initial velocity V. Then recall that the sine curvature at P, it was defined just to be this coefficient. So the acceleration vector lies in the span of the normal vector, right? And this coefficient is just going to be the sine curvature. In other words, it's the scalar projection of this acceleration vector onto the normal vector, so we can just get it by using inner product. On the other hand, we claim that this inner product is actually just going to be equal to the inner product of this velocity vector with this. In other words, it's equal to the inner product of our original vector V, right, with a negative of this n dot at 0. So why is that? Well, this really just comes from the product rule. Observe that the velocity vector field and the normal vector field should be orthogonal to each other, right? So that means that the derivative of their inner product should also be 0. But by product rule, this is just the sum of the following inner product. So the inner product of acceleration with the normal vector plus the inner product of velocity with this n dot. This means then that the inner product of the acceleration with the normal is just gonna be equal to the inner product of velocity with a minus of the n dot. And this is exactly what we claim here. Thus we see that our curvature map here sends every vector v to this inner product. We thus define this vector to be the value of the shape operator at v. The shape operator is a linear map from the tangent space to the tangent space at p. And if we define the shape operator as such, then we immediately see that this map is just given by v mapping to the inner product of v with its shape operator. Now, because of our notation, you might be a bit confused because it looks like here that this has nothing to do with v. It seems that it's constant independent of v, but that's not quite right. Observe that this notation only makes sense if we have fixed a plane. Right, we have fixed this plane, and on that plane we view this curve as a planar curve. In particular, when we talk about n dot here, we are talking about the change of this velocity vector field, but in the direction of v. So the direction of v is implicit there. So this name here is actually quite apt because this shape operator of v, right, this vector here, tell us how the manifold curve in the direction of v, because that's going to be captured by how the normal vector moves, right, in the direction of v. So the shape operator captures how the manifold curve in the direction of v, and then if we want to know how much, if we want to get a scalar quantity out of it, we can just look at the scalar projection of this shape vector, right, in the direction of v. Now from this definition, then we see that if we define the principal curvatures to be the max and the min of this inner product, then they must be eigenvalue of the shape operator. And why is that? Well, if v is a unit vector, this inner product is just going to tell us the scalar projection, right, of SV in the direction of v. And this is biggest when SV and V are in the same direction, so it's biggest here, and it's smallest when SV and V are in the opposite direction. But in both cases, thus in other words, we see that this inner product, this scalar projection, is max or min if and only if SV and V lie in the same span. But that's just another way of saying that V is an eigenvector of SV. And in those cases, the scalar projection is exactly this coefficient alpha, so it's exactly the eigenvalues. So the max and the min of this inner product is exactly the eigenvalues of this operator. Alright, so that's the intuition behind the definition of the shape operator. Next, we want to define it more formally in a way that is general enough to work for a general Riemannian manifold. And to do so, we're gonna introduce the second fundamental form.